Maybe we can get started. Today's seminar speaker. She comes from the National Institute for Nuclear Physics in Florence. And let me first give a brief CV of her, summarizing her scientific career. Maria got her university education from Pisa, which was followed by a National Training Fellowship with Giorgio Parisi. After that, she held several postdoc fellowships, among them in Urbana-Champaign, where I actually first met Maria. She was working at that time in the group of John Kogert. After that, she held several postdoc positions in Jülich as well, where we met again, because I had a joint appointment between Jülich and Urbana-Champaign. Then she also went to Bielefeld for a while, and since 2002, she's a senior tenured INFN scientist, and she's currently working in Florence. She has held several guest professorships, one in Berlin at the Humboldt University, another one in Bielefeld, and she has also served on many scientific committees in the past. Among them, she was a board member of the scientific board of ECT STAR, and at present, and I'm particularly very proud of that, she is a member of the advisory committee of the Collaborative Joint Research Center funded by DFG in Germany between Darmstadt, Frankfurt and Bielefeld. Her research interests lie in the field of finite temperature field theory in a broad sense, and in particular on the numerical evaluation of the phase structure of certain theories, in particular QCD. Maria, the reason why I invited her is she has written recently a very nice article together with Anton Drunin about the topology and axions in QCD, which has, as I said, prompted me to invite her. I like this article very much. It's written very pedagogically. And as you know, axions are currently discussed as a serious candidate for dark matter in the universe, and therefore this is an important and timely topic. So Maria, thanks very much for agreeing to give the seminar, and please, we enjoy your talk.
Thank you very much, Jochen, for this very nice introduction. It brought back many nice memories. And thank you for having me here to give this talk, and thanks everyone for listening. These are very complicated times, and so it's very nice still to have the opportunity to meet colleagues, even if just only via web. So as Jochen, as the director, has already anticipated, this will really be an overview talk in which I will try to give you the flavor, or where do we stand on the topics of the title, so the connection of topology and axions within strong interactions. So it's really heavily based on this review that we have prepared with Anton Drunin. And also, although I will cover lots of work by other people, other workers in the field, but I still wanted to enlist my own recent work also with other collaborators, and I'm really grateful to them. I also want to say I'm particularly happy to discuss about this argument here in this ECT STAR series, because really at the very beginning of my interest in this specific subfield of strong interactions, I have organized a workshop at ECT STAR that was, I think, 2017 or 18, I think, with Alessandro Mirizzi. And that was really very inspiring. And probably most of my work has been really motivated by this workshop. Okay, so let's start with repeating what Jochen has just said, that we know that we should have dark matter. Is not the atoms only make, so the baryonic matter only make a very small fraction of the matter in the universe. And there is a very serious candidate to dark matter, which is the QCD axion, that of course I will motivate more in the following. But just to start from the end, if you wish, this is the, so what do we need to know about this candidate? So basically we need to know, well, whether it exists, but we need to know its mass and coupling. And the reason for this is that the different experiments, there are different experiments looking for this particle, but experiments are tuned to search the axion in a very specific range of masses. And so it's important for the experimentalists to have some input from us, from the theory, on what the axion mass limits may be. And also there are many different kinds of axions, basically, besides the one I will discuss. And so once we have limits for one particular kind of axion, once these axions are indeed discovered, one will be able to know more about the underlying theory. So this, I copied this figure from a recent overview of the Mad Max collaboration. I believe Andreas Ringwald was mostly taking care of this. And the axion we will mostly interested with is the axion which forms cold dark matter, so behaves as a cold fluid, almost a condensate. And I will, of course, say more detail later. And basically, the lattice topology that I will discuss, the role of the lattice topology calculations will be to tell us about these limits. So the mass limit of the variability, the possible variability of the axion when this behaves as a cold dark matter. So that would be the idea, but it's important to say that topology in strong interactions is also a very well-defined problem within the physics of strong interactions. So it's interesting per se. It has, although it may seem a bit of an exotic subject, probably most of you are not working in these things, young people, and it's a pleasure to have young colleagues. So it may sound a bit of some of the young colleagues may seem a little bit of an exotic stuff, but it's also important to know that topology has important phenomenological implication on the hadron spectrum and on the characteristics of the transition in QCD, of the transition to the quark-gluon plasma. And so a part of the talk will be really devoted to discuss these aspects. And then at the end, I will come back once we know about the topology in QCD at high temperature, and then we can come back to the implication on the axion. So now it's a topological charge. Now, if I start with the QCD Lagrangian, it's we know, I mean, at theoretical level, that it is possible indeed to add this further term to QCD that is f mu nu, so the tensor f mu nu twiddle, and it has been noticed many years ago already that this term has really topological nature. So it is something which is stable under small deformation. So it's a local term, and once you integrate this local term over all the space, it's often called the butterfly, if you think how these fields work together. And if one integrates over all the space, it really tells us about properties which are topological. So one can define a topological charge, which is indeed this integral of error to be as a sum, thinking about of a lattice, in which this term is defined on the lattice sides. Now, interesting aspect of this term, so written, one can easily recognize, for instance, it may be transcribed as a scalar product of magnetic to an electric field. And so this term violates CP, which in principle would be so even very welcome, because indeed we have CP violations in the standard model. And so in this sense, the strong interactions will go on the same footing of electroweak theory, in so much that CPT will be conserved, but CP violated. So how can we measure somehow the amount of CP violation? Well, the way this is done is via the neutron electron dipole moment, which can be computed within QCD sum rules and within chiral perturbation theory, with very similar results, and of course depends on theta. So when there is no theta, no neutron electric dipole moment. Now, experiments have been continuously measuring this quantity since many years, and it's very interesting. Results keep on coming out better and better, more and more precise, and they steadily go in the same direction. So this limit becomes stricter and stricter, and theta becomes smaller and smaller, and nowadays we know that this angle theta should be less than the number that you see here. And then, okay, there isn't, you say, we may take a pragmatic attitude and we may say, this is a number like another, but it seems very strange that nature has selected a number that is so close to zero. And so people wonder, maybe this is really exactly zero, and there is a good reason for this. And so this is called the strong CP problem, in the sense, do we have reasons to believe that maybe theta is exactly zero by some symmetry argument? So how can we attack this problem? Well, first of all, accepting that theta is there anyway, even if average value is theta is zero, but we can still consider this as a parameter of the grand canonical partition function. Then the grand canonical partition function of QCD will have an explicit theta dependence. And the way we can characterize basically this dependence on theta is via the cumulants of the topological charge. So by just a very simple manipulation, we will basically recognize that the Taylor expansion of the free energy can be written in terms basically of the momenta of the topological charge, which is again defined as the integral of F mu nu F mu tilde, which is the extra term, the theta term of the Lagrangian. And it's interesting to notice that indeed, since theta is so small, in any case, the relevant quantities will be the cumulants measured around theta equals zero. Again, how can we learn about these quantities besides numerical calculations? Well, chiral perturbation theory is really extremely powerful in this field, and so one can measure can compute the theta dependence in this way of the free energy. And actually this is a leading order, but has been recently improved, and we can also see that this is really stable, and probably these are the best results quantitatively at zero temperature. Of course, chiral perturbation theory holds is correct only at very, very low temperature. Zero, low, can be pushed close to TC, but certainly not at the critical temperature or beyond. Now, at very, very high temperature, on the other side, there is high temperature perturbation theory is a good guidance, and together combined with Deloitte instanton gas approximation, and this gives this other parameterization for the free energy. And basically this single cosine, in a way that we can elaborate, but basically is telling us that only sectors with unit topological charge are contributing to the partition function. So these are the two limiting cases that one can study. And in the middle, we don't really know what happens. Now, again, what we notice, but to come back for a moment to the strong CP problem before discussing the properties of F theta and T around TC and in the region of interest, to come back to this, to understand why perhaps theta may be zero, one may draw these two limiting cases. And then we can see that both instant-on liquid, dilute to instant-on gas, or chiral perturbation theory have indeed a minimum at theta equals 0. However, this is not really solving this observation, the strong CP problem, because at this stage theta is just an external parameter, so it can be whatever. It doesn't mean anything if the free energy is at a minimum or not a minimum, it's a number, can be readjusted. But now, so the solution was found by assuming that trying to promote theta to a dynamical quantity. And basically one imagine a new field, the axion, which couples to QCD in this way. So then the total Lagrangian would be the QCD Lagrangian plus the axion term, and the axion term couples to the topological charge as QCD does. So in this way, the global effective potential somehow of QCD is controlled by this combination, not just theta, but the axion field divided by the axion coupling and the old theta angle, but which is absorbed in this general value. So what we really see is this total value, which is dynamically set to 0, because the effective potential will have to be at the minimum. At this time, it will be dynamical statement. So this is somehow the solution of the strong CP problem as proposed by Pecei and Quinn and further elaborated by Wilczek many years ago already. Now, the same chiral perturbation theory which was used to study the potential before, one just repeat things, and this time finds a statement about the axion mass. And the most important finding that will be very central in this talk is this relation. So the fact that the square of the axion mass times the square of the coupling is equals the topological susceptibility. So this is somehow already explains a little bit these two scales that we have in the plot, because we know that the mass times the coupling of the axion should be the square root of the topological susceptibility. But what we don't know and what do we need to constrain the mass is some argument used to constrain the amplitude or vice versa. So we know a relationship between these two. So we know simply this is correct, but we cannot extract the axion mass from this relation unless we can constrain the coupling. And the exercise that one has to do is to find the argument by studying the cosmological evolution of the axion field, to estimate the current density of the axion and to see which is the acceptable range of parameter which makes the density of the axion compatible with the observed amount of dark matter in the universe. And that's what we will do towards the end. But now we want to then focus on extracting information on topology. So to summarize what was sketched above, we have the topological susceptibility as defined in this way from the free energy, which is nothing but the fluctuation of the topological charge. In chiral perturbation theory, one can get some form. Well, I did it very badly, so it doesn't go back this way. It was my bad drawing. So chiral perturbation theory, which describes topological susceptibility at low temperatures, there is a very high temperature limit, and one issue is how large is large, for which temperatures we start trusting this approximation. But in the middle, there is lots of activity, possible activity, mostly by lattice QCD, but also by models, because it's interesting to contrast, compare with models, and holography. There are interesting calculations in holography as well, and so on and so forth. Now, I just would like to make sure that, can you still hear me properly? Maybe I should have asked before.
Yes. Yes.
Do you still, can you repeat? Do you still hear me?
Yes.
Ah,
yes.
Good.
Yes.
Thank you very much. I was asking, but I didn't have the headphone on, so I could not hear the answer. Okay, sorry. Okay, so let me continue.
Just a question. So this dilute instant goes to zero for temperature?
Sorry?
The dilute instant on curve goes to zero for
Yes. The dilute, eventually it will go to zero, and the functional dependence will be a power law in temperature, and much of the activity will be, or part of the activity will be in understanding when the correct decay exponent of the dilute instant on gas will be reached by the lattice data. But definitively, topology will have to disappear in the large temperature limit, just because somehow the free field can't have any real topological structure at high temperature. Yes. Now, how do we handle then this problem on the lattice? And then on the lattice, I don't want to bother you with any lattice detail, but you probably know that lattice is calculations relies on importance sampling. So we don't compute all these integral, but we select in some way a significant sample of gauge configurations. But for this to be possible, this way it has to be positive, definitely it has to be positive. And what happens is that if I include this theta term, it's very easy to see that once I go to the Euclidean space, as we have to do on the lattice, the theta terms becomes complex. And so the importance sampling, which is needed to evaluate the lattice integral, this integral on the lattice, is no longer possible. So what one can do, as I already mentioned before, is to measure everything around theta equals 0. And so one does the simulations at theta equals 0, but one measures the fluctuations, and from the fluctuations of topological charge, one can reconstruct various moments. For those who follow quark-gluon plasma, this is a similar calculation, similar logic, and similar spirit of what it is done to compute baryonic fluctuations in the plasma around this LAC working region. So we know that the chemical potential is very small, so we can compute the fluctuations, and staying at mu equals 0, and here is exactly the same. We try to compute fluctuation sitting exactly at theta equals 0. As an aside, I cannot avoid mentioning this, though. From a purely theoretical point of view, theta equal pi is certainly interesting to push physics beyond theta equals 0. But so I mentioned this to be complete, because I don't want to say that only theta about 0 matters. There are very interesting theoretical works at theta equal pi in particular, where CP is no longer explicitly broken, but maybe it is spontaneously broken, and people use this to model bulk building, but it was really an aside. I want to follow up on this. Now let me discuss how topology is involved with symmetries and spectrum in QCD. So, and this is again, I wrote explicitly the Lagrangian of QCD by isolating the contributions which are relevant for the flavor symmetries. And then we know that when in the chiral limit with 0 mass, the Lagrangian is invariant under this UN rotation. And so the Lagrangian enjoys a global symmetry, UN left cross UN right, which one can exactly decompose in the simple unitary symmetries and U1 symmetries. Now, you know that this SUN cross SUN is a spontaneously broken symmetry of QCD, which originates n squared minus 1 Goldstone boson. So when we consider SU3, we have these 8 Goldstone, pseudo-Goldstone bosons. And U1 vector is the baryon number, so we won't touch it anymore. So I forgot about baryon number from now on. And now there is this axial symmetry where it's really the one which is more interesting to us, because we will see that it is explicitly broken by quantum fluctuation, but why? And now somehow that's a connection to some extent between topology and phenomenology, because if I consider the axial symmetry, that's just a simple rotation of the quark field, and this symmetry will be broken by the spontaneously generated chiral condensate, the one which is generated by SUN cross SUN breaking. And then this candidate, this eta prime particle, will be candidate to be a Goldstone boson on the same footing as the other Goldstone bosons. But this is certainly not true, because the eta prime is too heavy to be, it should be a similar to the eta meson, basically. Now, which is the way out and how this is solved? Because if one considers the divergence of the associated current of this symmetry, we see that this divergence contains a mass-independent term. So even in the chiral limit, this current is not really conserved. Okay, it's not conserved if this integral is different from 0. This was theoretically very difficult, because at the first inspection, one says, but it doesn't really matter, it should always integrate to 0. But then it was, that was how it was realized, that exactly because it has a topological nature, because of topological fluctuation, this may well be different from 0. And when this is different from 0, this axial symmetry is explicitly broken, so the symmetry is anomalous, and when it is explicitly broken, eta prime is no longer a Goldstone boson, and it gets a mass. So this is the kind of experimental evidence for the breaking of the U1 axial symmetry in QCD. But of course, we also like to have more theoretical proof of this, which is also a way to establish the role of topology in phenomenology. So first of all, important observation, somehow called Atiyah-Zinger theorem, is telling us that this definition of topological charge, so this identification, so it's not a definition, but this identification of this term with a topological object can also be rewritten by appropriate manipulation in this form. So the topological charge, the total topological charge, is also the difference between the negative and positive fermionic zero mode. So indeed, the topology is a field in which gluons and fermions really communicate in a very clear and transparent way. This is to me, one of the most interesting aspects, because sometimes when we discuss chiral symmetry, it's pretty much also in the transition. When we discuss chiral symmetry, that's pretty much fermionic object. When we discuss confinement, it's pretty much gluonic property. But when we discuss topology, this is really at the heart both of gluons and fermions behaviors. It's very interesting. And the eta prime mass, having made this identification, may be computed in two different ways, either as a correlator of this current, the axial current, or via the correlator of the gluons. At the leading order, the mass of the eta prime, just by exploiting this relation, is given by the Witten-Veneziano formula. And this is well proven at t equals 0. So if theoretically I want to convince myself that eta prime mass is really very much tight with topological objects. What I have to do is to measure eta prime in this way, and this has been done at t equals 0. Very nice work by the European Twisted Mass collaboration, based mostly work done in Bonn and in Zeuthen by Karl Jansen, Karsten Urbach, and collaborators. And these are the eta and eta prime mass at 0 temperature. These are all lattice technicalities, but the real results, so on the lattice we change the pion mass for several reasons, so we have then eventually to extrapolate to the physical values of the pion mass, and these are the extrapolation to the physical values of the pion mass, and these are the experimental values of the eta and the eta prime. So you really see this excellent agreement and full control over this t equals 0 explicit breaking. Same thing, just by reasoning on the Witten-Veneziano formula, one may search for a similar evidence by measuring the topological susceptibility in Ian Mills. So this is a very nice calculation by Luigi Del Debbio and Leonardo Giusti as a function of the lattice spacing. On the lattice, very important to get continuum limit, and S is a technical parameter for these measurements. So they did the measurement with 2 values of these technical parameters and for different values of the lattice spacing. And the logic is that in the continuum, all the definitions should give the same results, and they give the same results, and it translates to this value for the topological susceptibility. To complete the overview, even in full QCD, also in full QCD, the topological susceptibility has been computed. This is the TMC calculation, the same of the eta prime. This is another calculation from the PISA group. And in both cases, the results this is in Fermi and this is in MEV. So the results are perfect in agreement. And so everything gives very good confidence that in the low temperature phase of QCD, we have a very nice control over topology. And also note this excellent agreement with the prediction of chiral perturbation theory that I was showing before. Now, having discussed the pattern of symmetries in the 0 temperature regime and their interrelation with topology, we ask the question, what happens in hot QCD? And so that was a very nice paper by Shuriak in which he was posing this question, and after many years the question is still not completely answered, even if many workers in the field are addressing this. Now, concerning this part is very well studied. So SUN cross SUN is really very well studied, and its breaking and restoration is really, I mean, we know what happens in this sector. We know it is restored. Let me put it this way. We know that we have understood that this is broken by fluctuations of topological charge, but the question is, how are these fluctuations affected by temperature? And so normally we expect that, so we don't know really, it's a really dynamical question. And so the question is also, how are these things related and which are the phenomenological implications of the relation? Again, this has been studied in chiral models, and these are somehow very suggestive. This is the behavior of the topological susceptibility studied with their methods, and also similar results. So this is really very similar calculation. Indeed, maybe there are some small differences, but it's really very similar to this parametrization of the topological susceptibility in full QCD, which may be indeed related directly to the behavior of the chiral condensate. So if this relation is true, indeed, one would have chiral symmetry, which is really driving also axial symmetry, and these two symmetries will be really very closely interrelated. So the question really in physical terms is whether one has different physical mechanisms behind these two symmetries. And of course, if one really strongly believes in instantons and all these models, indeed these two symmetries are a bit two different things. But if one perhaps follows, maybe that's a really oversimplification, but if one follows the logic of the old Veneziano Witten work, like UA1 without instantons, then one has really no much room for playing, and chiral symmetry and axial symmetry would be perhaps a very entangled phenomena. But we really still don't know. So how do we attack this problem at a practical level? So this is, has been studied by Pisarski and Wilczek, and more recently by the PISA group, where they have really arrived at the same results and also made them more precise. And what we know is that if the axial symmetry is insensitive to the chiral restoration, then all matters is the restoration in the light sector of the SU symmetry, which in isomorphic language would be pattern of breaking of 4 to 03, and this pattern is very well studied, and we know everything. It's a second order transition, we know the exponents, we know the universality, behavior, and all that. If instead the axial symmetry is restored at EC, one possibility is that this is a first order transition, or maybe there is also this possibility for this other universality class, but certainly distinct from this one. So which is the strategy? That one studies, one way to study the problem, since again the measurements on the lattice are done with a finite quark mass, because of course all this analysis is true in the chiral limit, but we do measurements with a finite quark mass, and so we measure the pseudo-critical temperature with different values of the quark mass or of the pion mass, which is of course the same. And if we look at quantities, really pseudo-critical temperatures measured from the peak of the relevant susceptibilities, for instance, we would expect this kind of scaling. This equation is wrong, many apologies. This T here is M pi. Sorry, it's not T. So we are, sorry, I see it now. So we are studying the scaling of the pseudo-critical temperature as a function of the pion mass. So this is the pseudo-critical temperature at 0 pion mass plus a term which depends on the pion mass with these exponents. And one should compare with exponent with the anticipated universality class, and maybe with scaling violating terms, if I consider behavior of pseudo-critical temperatures. So the other strategy, I can try to work with scaling invariant quantities and define a critical temperature by using RG invariant quantities. And if I use some RG invariant quantities, then the critical temperature should be mass independent by definition, and this could be another strategy. And these two strategies are shown here in this plot, which I took from the very nice review presented by Anton Ding at the recent Quark Matter Conference in Wuhan on behalf of the Hot Qcd collaboration. So these are results for the pseudo-critical temperature for the first strategy, in which we try to see the scaling of a pseudo-critical temperature with the pion mass and compare with O4 scaling. And these other objects are a pseudo-critical temperature extracted from RG invariant quantities. I think basically he was considering the ratio of the transverse to the longitudinal susceptibility. And this should be constant in case of exact scaling, and there is a small residual mass dependence that one can parameterize. So all in all, this here I have also the information on the exponent, and very well consistent with O4 scaling. And in both ways, this estimate in the chiral limit extrapolate to very similar values. So this is a proof of consistent, but already you can see that from these very large errors, one may still have a different results, because also other parameterizations will not be so different. And in particular, there is a very nice work within functional renormalization group by Hans Braun, Jan Pawlowski, and other collaborators, Fabian Rennecke, and they made a very convincing case that indeed it's impossible to see any true, genuine critical scaling unless the masses are much, much smaller than this one. And so whatever we see here, they argue, is not the real scaling, and so one can't really trust the extrapolation. So this is something that we are really, in our group, we are discussing with them, and we try to understand better. It's a discussion in itself, but just to say that the question is really open, and topology, of course, plays an important role in determining the various universality class. Maybe I skip this one, very interesting. Another way to attack more directly the kind of symmetry which is restored is a very direct comparison of the degeneracy of the different mesonic channels. So if I build operators in these different channels, some of them are related by SU2 cross SU2 symmetry, for instance, the sigma and the pions, and others by the axial channel. So by studying the degeneracies of in these different channels when when increasing the temperature across the phase transition, one may assess which symmetry is indeed restored. Now, there is a consensus that axial symmetry is effectively restored above 1.2 Tc, in the sense that operators built by using all these channels become all degenerate. And so one say, okay, above 1.2, apparently, I hope I haven't misinterpreted, but my reading is that everyone agrees on that, these authors. But there is still a controversy still open, how close to Tc this effective restoration may happen. And so I should quote exactly the same reference as above, because everyone is happy to say that the axial symmetry is restored at 1.2 Tc, but it's not so clear where exactly. This was an example of how one can look at this. These are these different channels, mesonic, computed in old paper with instant on liquid, but these are the calculation, recent lattice calculations, for instance, and they show, in this case, this is the relevant order parameter for the axial symmetry, and for instance, according to their conclusion, this should remain broken exactly at Tc, because you see that this breaking parameter does not depend on the mass here, so it seems to be different from zero. It will remain different from zero also in the chiral limit by looking at these results, but then it will go to zero later on. And we have preliminary results here, which instead say perhaps something different, in which they remain, I'm sorry, I say something stupid here. I don't know, they say exactly, in our case, we say the similar things in the sense that remains broken around Tc. But other workers have different conclusions, so I'm not going through a full review of this, but just point out that this is indeed an open problem at the moment. Now let's focus on topology itself. So these are sort of indirect measurements of topology, in the sense that the pattern of symmetries is related to that, but then we ask really the question, what happens to topology in the plasma? Now, as you can easily imagine, measurements of topology are a bit delicate, because when I discretize, normally, because topology is related, has to do with quantities which are robust under a small deformation. But once I have discretized my lattice, nothing is robust under a small deformation, because I have cut my space. So there are, that's a very hand waving of putting this, but in a nutshell, that's the reason why lattice topology is particularly complicated. But nonetheless, one can measure it. It's just to explain why it's so much behind other calculations. So one can do just to translate the gluonic definition of the operator, and just rewriting this with some technical refinement. So this is easy, but it's really the worst you can do from the point of view of lattice artifacts. Otherwise, one exploits the Atiyah-Zinger theorem and uses this relation and counting positive and negative zero modes. And clearly, that's very, very expensive. by definition is not much affected by ultraviolet fluctuations, because the zero modes are more infrared properties, but at the same time one has to do all the counting, which is very expensive numerically. Then there is a very simple and approximate way, which to my knowledge has been introduced by John Cogut with Jean-François Laguet, Don Sinclair, but applied very seriously for the first time within the Hot Qcd collaboration. Yeah, perhaps one reference should be added by Norman Christ and collaborator in 2012, and then Petrescu Sharma, and then by us later. And then by doing some manipulation of this identity, one arrives at this identification which is valid in the quark-gluon plasma. So this is exact. Topological susceptibility related with the axial disconnected susceptibility is exact. And in the quark-gluon plasma phase, the axial disconnected susceptibility is the same as the normal susceptibility. And so the measurement of the topological susceptibility is basically just a measurement of the fluctuations of the chiral condensate. So that's another technique easier. So results in Yang-Mills, in which, of course, Yang-Mills. So first of all, analytically, what does one know? So again, this is in more detail, the results from the diluate instant-on gas approximation with some corrections. And what one finds is that the topological susceptibility decreases at larger temperatures as a power law in temperature with these exponents. The K are different renormalization scales. It's reasonably stable with renormalization scale, and it has this slight increased trend with temperature. Now, if I look on the lattice, the exponent reaches quite soon, so around 3Tc to 3Tc, the prediction, the analytic prediction, but there is one order of magnitude discrepancy in the absolute value of the topological susceptibility itself. And this remains a bit of, again, open question. I mean, it's not so strange because the strong coupling constant in this range is still quite strong, so it would be surprising to find a perfect coincidence, but still it's a bit surprising that we reproduce perfectly the exponent, and still the amplitude is so much wrong. So I don't know if the experts maybe in the audience on the QCD and perturbative QCD have further comments. So at the moment is just an observation that a numerical observation, but well verified. So these are more details in the calculation that you have just seen. Beyond topological susceptibility, remember that one in principle may like to reconstruct the entire free energy as a function of theta, and the topological susceptibility is just the first term. So interesting indicator is this B2, and this is interesting because this combination will be exactly zero if the distribution was a plane Gaussian. And so one measured the distance from the plane Gaussian very clearly, and then check how the Diga results is reached by knowing the expression for Diga. Now, it's very nice. So in the continuum about 3Tc, one reproduces the Diga result, but I mean, to be honest, it's very nice, but not so fantastic, because in the sense of what is telling us this quantity, if we look how this B2 appears, is basically confirming that the potential is as a cosine form, but the potential as a cosine form when only instanton of plus minus 1 contribute. So this is just a statement that when we arrive at this point in temperature, only instanton of unit charge contribute to the partition function. So it's an interesting statement from the point of view of instanton liquid, but it doesn't tell us much on the dynamics at this stage. But still, it's a nice agreement, and that's why I'm showing it. Very interesting technically, perhaps not so interesting for people not in the lattice, but wonderful idea by Martin Bluscher applied here is the so-called master field simulations. So master field simulations to some extent go beyond importance sampling on the lattice, because they try to find so they use the self-averaging property of large systems. And so you find very large volumes, and in a very clever way, you measure everything just on one lattice, so roughly. But anyway, they did the measurement for topological susceptibility with this trick for 2 temperatures, which is very useful for general comparison. So this is a summary, quick summary of the status in Yang-Mills. And the different groups are in a very nice agreement. So these are the results by Giusti and Bluscher that I was showing to you before. And note this very, very nice agreement with the results from the Wuppertal Budapest group, really perfect. There is an early study, seems a little bit in limit here. So indeed, the situation is really very gratifying. There are some results, some attempt by Guy Moore and collaborator to improve on methods. So they still have these very large errors. I think they have recently completed another paper. But so at the moment, if we just look at the results, at the best results, the most trustworthy result in the sense continuum limit and large statistics, you see Gattringer, Wuppertal Budapest, Bluscher, and so that's, I want to say, very satisfactory situation. Now, what happens in full QCD? Well, I want to start with these very interesting results by the BNL group. First of all, how much time do I have? 10 minutes still?
Yeah, about 10 minutes.
Yes, okay. Good. So this is the results by this group, in which first they were comparing between different methods. And so the fermionic and this simplified fermionic method that I was mentioning, and the agreement is really quite good. And they were also comparing with the approach to the Giga limit, but after rescaling though of the value, because this order of magnitude discrepancies still remain. This is interesting, all the results, but still with comparison between gluonic and fermionic methods. So that's lattice technicalities, but just to confirm that these two methods work well together. And this is probably let me see if I have, no, I want to show this. This is a result from probably the best result, the best study, the most complete study that we have so far still, by the Wuppertal Budapest group, in which they used really very different methods, very different techniques. Of course, not everything completely under control, so this is why we should still have to cross-check to some extent. Again, they show this discrepancy as an order of magnitude between the Giga and the lattice results, but the lattice results are really obtained numerically in a convincing way up to 500 MeV, and then there is a good extrapolation to larger temperature. This is the exponent, the effective exponent for the decay of the temperature of the susceptibility, topological susceptibility with temperature, and again there is a very nice approach to the diluted Stanton gas limit. That's a really impressive range of parameters and methods from this group. So at least up to 500 MeV, really there is a very good control. And then some approximation or speculation. These are our own results compared with the Wuppertal Budapest group. And we use, since we were not exactly at the physical pi of mass, we were rescaling according to this form with a decent agreement. We will then discuss the impact on the axion mass of these results. And we also have preliminary results for the physical pi of mass, which compare decently with the rescaled results at higher masses. Again, we check whether we reach this power law decay at large distance with T. Sorry, in this slide, I use D. In other slides, it's called B, but here it's D for this exponent. I hope there's no confusion. And then we see that this D exponent is really reaching, again, the instantant limit above 350 MeV in agreement with other authors. Now we also have this smaller temperature in which we see that the exponent is a bit larger, and this is compatible to some extent with this instanton dion prediction by Shuriak, and so probably something to work more about. Again, this is a complicated region which is still not completely understood, but again we confirm that above 350 we approach this nearly free behavior. There are several issues on the lattice on the continuum limit, but really several studies demonstrate that the continuum limit is under control, so I won't elaborate much on this. So this is the summary of, I believe, rather complete summary of all the calculation in full QCD with physical masses, in some cases with some rescaling in our case, but so we believe with physical, these are the physical results for the topological susceptibility in QCD as a function of temperature. And you can see that some very coherent scenario is really emerging between different groups, but still there is a little bit to work to arrive at the level of accuracy of other lattice calculations. So the situation is interesting, but is nice. In some cases, we will see that when we compute the axion mass, these residual differences are not so important in the end, because the dependence will have lots of force, root, and logarithms. So in the end, these differences, even of one order of magnitudes, will not make much difference in the axion mass. But still, from the point of view of strong interactions, we hope to reach a more robust final conclusion. And this is for QCD. Again, the same statement can be made for this decay parameter B. So this is the fit. These are the results for the fit of the temperature of the decay of the topological susceptibility with temperature. This is a minus at large T. And again, there is it's not a real discrepancy. So when temperature becomes large, for these are estimates for rather large temperatures, and then the results from the diluted instanton gas are very well reproduced. For smaller temperature, one is not really there, but is getting close, as perhaps one can see better by following the temperature dependence here. So that's for topology in QCD, that's the status at the moment. Now, I want to say a few words of what happens to the eta prime, that was such an important probe of the axial behavior in the plasma. Was papers talking about the return of the prodigal Goldstone boson, because at high temperature, if the axial symmetry is restored, eta prime goes on the same footing as the other mesons. And amazingly, before we started, the only model results were available. And for instance, one can see from models that indeed the eta prime behaves close to the other mesons above TC. But again, the dynamics is important. So what we really want to see is what happens to the anomalous contribution to the eta prime mass. So if I try to measure in some model, just to get a feeling, the value of the eta prime mass, I can see that what splits basically the eta prime, following the previous reasoning, from the other mesons is the topological susceptibility. Without this term, the eta prime will be an SS bar state. So basically, if I want to see what happens to this contribution in the eta prime, I have to compare the eta prime with an SS bar state. And before doing this on the lattice, I just also want to show you some indication, indeed, of topology suppression in the Phoenix experiment, in which they compare their data with models with different values of data prime and really find compatibility of the data with the reduced value for data prime. So they have an indication in Phoenix of topology suppression from the experiment. Now, this is the results from the lattice. So this is the non-anomalous contribution to data prime, so the SS bar state. And then, indeed, we see the data prime is losing the anomalous component and reaches this SS bar value corresponding to the disappearance of the anomaly. And this happens in good correlation with in this case, we have an indication of a correlation of disappearance of the anomaly with the chiral restoration. So these results will suggest that the anomaly disappear at the same time as chiral restoration. Again, contributes to the scenario still building. Now, the last thing I would like to tell you, so we have seen that this strong CP problem can be solved by introducing the axion, and we have derived or mentioned briefly this relation between the axion mass and the axion coupling. Now, how do I put constraints on the axion mass by looking at the topological susceptibility? Well, the key observation is that what happens, axions are produced at some point in the history of the universe at the time of the breaking of the Peccei-Quinn symmetry, this extra symmetry which has been added to the Lagrangian of QCD to solve the strong CP problem. Now, for a while, the axions make their own evolution in the plasma, but at some point, basically, the mass of the axion becomes comparable with the Hubble parameter. After that time, and this emerges from the solution of the equations that I want to review here, but after that time, basically, the gas of axions behave as a cold gas. So there is no more thermal behavior, and the density to the entropy of the axion after this time remains constant. So if I can find the time of freeze out, I know that the density to the entropy of the axion remains the same, and it will be the same as today. Since we know the total entropy today, once I know this value, I can compute the contemporary density of axions from this value. Just I simply multiply this value here by the contemporary entropy. So all I need to know basically is this freeze out time, and then I can compute in a parametric form the axion density, and I can compute this axion density with the observed density of dark matter. Now, example of calculations. Again, this is a calculation of axion freeze out by the early study by Berkowitz, Buchhoff, and Rinaldi. They have been the first one to do this application of lattice to cosmology, still with quenched data, but very useful for illustration. And so they have been computing different freeze out times according to different choices of the axion coupling, because of course what mapped. So this depends on the axion coupling. And this is the same calculation one can repeat with full QCD. So basically, this is the recipe. There is an axion, the axion freeze out, the first step. After freeze out, this density is constant. I can then compute the axion density today in this form. Putting all together and taking into account various cosmological constants, one finds this dependence of the contemporary axion density on the axion mass in this form. And this parameter B, which enters here, is exactly the B parameter of the decay of the topological susceptibility at large density and at large temperatures. So this is the axion density in a parametric form as a function of the axion mass. I can then plot this for illustration, and let me spend a moment to explain a bit this plot. So first of all, I know the fraction of dark matter. So I know the upper limit of dark matter. I know that if axions make dark matter can't be more than 24% of total matter. So I have a very well-defined upper limit. I have a density of axions in parametric form, and I certainly know that this density that I will extract from my calculation cannot be more than 24% of the total density. So this is the contribution, this is the fraction of axion density, the total axion density defined in this way. I just use this rho c as a normalization, but this is basically the axion density, contemporary axion density. And I know that this ratio, a maximum, can be 1. So when this ratio is 1, this is a so-called overclosure bound, and this means that axions are taking all possible dark matter. Now, these different lines, the green lines, I'm using my own result, our own results as illustration, but other groups have very similar strategies of analysis. So these are my central results, the ones that I consider my best results, obtained with the pions of 210 MeV rescaled to the physical values. So if I trust my best results, I would read off that if the axion makes 100% of this green line, the minimum axion mass that I read here will be some 30 microelectron volt. I want to know how important the errors are. So what do I do? First, I use also other calculations, still mine, and I see that more or less I remain in the same range. If I really want to exaggerate, I start playing with the exponent, and I see that if I use the exact exponent from the diluted instanton gas, I still remain quite close. If I play with the amplitudes, so suppose that I was very wrong with the amplitude. You have seen that we have this factor 10. Well, I am exaggerating. I am taking amplitudes even 10 to the 4 larger or smaller. And the variability is really modest here. It doesn't change much. What really makes a big difference is to use d = 4, which would be the estimate from very simple early calculation. So if I assume that the long temperature, the high temperature decay has this exponent, then I find an axion mass which is very, very low. Now, this is historically important because in early times, these were the only results available, and some experiments have been built assuming that this was a valid lower bound, but most likely we know that probably this is not the case. And so again, let me show that's another example, but should be rather clear if I think that if the axions are the 80% of dark matter instead, then the lower bound moves to larger value, of course, because if I limit the amount of dark matter, then of course I have to use heavier axions to make up all the clamps. So by putting together the results, by making similar analysis, by using all the results by the different groups that I have reviewed, we find this collection of values for the lower limits on the axion mass from lattice QCD. So these are our absolute lower limits. So the ones that we find by assuming that axions make up 100% of dark matter. So these are the lattice results, these 4, and I have also added another results by Claire and Moore, which is very, very interesting because, in fact, what I was saying, I have to assume that the axions make up all dark matter or maybe half of dark matter. So this I put just all of dark matter, but it's just a guess. But what is found, if we really study the evolution in the cosmological time of axions, at the moment that we start creating the axions, we also create domain walls and strings, and they necessarily contribute to the dark matter mass. So what
Maria, could you shortly come to the conclusion?
Absolutely, and is the last slide indeed. So what Claire and Moore have done, they have really computed this extra string contribution, and so they have this more precise value probably for the lower limit. So this is again the same calculation, so I don't need really to repeat, but basically as anticipated at the beginning, these numbers here are the lower limit of this post-inflection axion mass, and this is my summary that probably I can also leave it for you to read and ask whether there are maybe questions. So okay, thank you very much for attention.
So thanks very much, Maria, for this very clear and broad presentation of important questions, both in QCD physics, also in cosmology. Are there any questions or comments from the audience? Maybe then let me ask a question. Can you go back to this freeze-out formula for the axions?
This one you mean?
No, further. Yeah, this one. So h of t is the Hubble constant, right?
Yes, of course, the 3 comes out from the solution of the Friedmann equation with the proper, so this is somehow an approximate solution which comes from solving properly the evolution equation. So it's a bit, that you're right, it's a bit approximate. I think the proper calculations with all the factors, even in a simplified form, are in the original Vance-Schellard paper. This is a simplified expression that one uses here for the purpose of estimate. Yes.
But, you know, there are uncertainties in today's Hubble constant as well. You know this problem, that there are discrepancies for various ways of extracting this. Doesn't this have any influence on the axion mass as well, or?
No, I don't know whether this has been really, it's certainly not in the calculations that I have done, in the sense that the Hubble parameter, I used the standard parameterization with the counting of degrees of freedom, more or less approximated, but I haven't done, and I don't think that other people have considered further uncertainties. So that's very interesting, and certainly should be in a more sophisticated, for instance, in this calculation that Guy Moore is doing, where he calculates alongside with the mass contribution, also the string contribution. So in this calculation, probably one should also include the knowledge, more knowledge, or the variability of this Hubble constant. Certainly not here. Here is just very bread and butter, in a sense, what has been done.
Maybe then let me ask you another question. I mean, this phase transition in which the Paget Quinn symmetry is restored or broken, what is the order of that phase transition? Do you know?
No, because I don't know, honestly. Of course, the only thing which really matters for this transition, of course, that has been taken into account is it may affect indeed the kind of domain walls which are produced, because when the transition, of course, happens still during. So what happens is that the transition is symmetry is broken initially in some direction, along some angle theta, that's the initial angle, then if the transition happens during the inflation, all the theta angle are inflated away somehow, and one has just one initial theta angle, and this is one thing. If the symmetry is broken after the Peccei transition happens after inflation, then one can average over all the possible theta angles. Now, whether this transition, and so this is what really makes an important difference, and this is why, of course, we discuss most the post-inflectionary axial mass, where we can really put limits, because we don't have the variability in the theta angle, which makes otherwise things much more variable. Now, whether the transition is first or second order, it may make a difference in this string contribution that, for instance, Guy and others are computing. But I don't know, maybe my ignorance, it doesn't enter in this kind of calculation, I want to say. But then, of course, it's an interesting question per se, because also for generation of other effects like gravitational waves, or clearly any first order transition will have a much stronger implication cosmologically than a smooth behavior. But from the point of view of this one calculation, I don't think it's considered the order. Yeah.
Thank you.
Thank you.
Any other questions or comments?
So let me come back to the, so I can see you. Thank you very much for being here.
Yeah, so thanks very much, Maria, for a very nice and instructive presentation.